let us see another question from alkane series. This question is related to stereochemistry of the reaction and free radical substitution. And here one bromo derivative of alkane is given, and this is subjected to monochlorination. Already you have one halogen, bromine, but now this is subjected to monochlorination. You will get different products here. You will get different products, and about these products, some options are given. One is about total number of isomers. One is about fractional distillation of the product mixture, and about the chirality of the products and the chirality of fractions. So first let us take all structural possibilities. The given compound is a pentane derivative. You can see this is a pentane. Here you have one methyl group, and here you have a bromine, but that bromine, that chiral carbon has a fixed stereochemistry. There the stereochemistry, that is chiral, and its stereochemistry is fixed. So before reaction there was only one chiral center, and the main idea is we need to write all possible structural isomers. In every structural isomer, then we'll look into stereochemistry of the particular structural isomer. So in this, let us start from this end. You do substitution either here or here. Structurally they are definitely same, and whether they are structurally same or not, you just give its IUPAC name, you will understand whether they are structurally same or not. And here this is bromine, that is chiral. Bromine containing carbon is chiral, its stereochemistry is fixed. And here chlorine, at that position hydrogen is replaced, and this is the first possibility. This is the first possibility. Already I told you, you do substitution either here or here, structurally they are same. Now I am going to replace hydrogen at this center. At this center I am going to replace, and here you already have one methyl group. Let me write this, and here methyl group, and this is bromine, that is chiral carbon. Now we are taking substitution at this position. So here this is chlorine, free radical substitution. This is another structural possibility. Now let us replace hydrogen present at this bromine containing carbon. There is one hydrogen. We are writing all structural possibilities. So here this is methyl group, and this is bromine, and here we are writing chlorine. We are writing chlorine, but already told you we'll talk about stereoisomer of every structural isomer once all structural isomers are written. And let us move on to this particular center. At that particular center substitution is taking place. So here it is a 5 carbon chain. Here you have methyl group, bromine containing carbon, stereochemistry is fixed, and here you are writing chlorine. You are writing chlorine here. So here this is one structural possibility. And the fifth possibility, so we are taking at this position. So I am writing the fifth possibility here. So this is methyl, and here this is bromine, and this is chlorine. These are the structural possibilities. So this is the first one, this is the second one, this is the third one, this is the fourth one, and this one will be fifth. But most importantly, he is not asking only the structural isomers, total number of isomers he is asking. And if you look at the first one, already there is a chiral center and its stereochemistry is fixed. But here a new chiral center is produced, that is this one. When substitution takes place at this position, this is becoming a new chiral center. So already one chiral center is present with a fixed stereochemistry, and a new chiral center is produced. Therefore you will be getting plus 1, that plus 1 is a diastereomer. Diastereomer means, optical diastereomers means, at some chiral centers the configuration is the same, at some other chiral centers the configuration is different. So to avoid confusion, first let us derive the stereochemistry of this compound. So bromine gets the first priority, isopropyl group, second priority, ethyl group, third priority, and you are moving like this, and you are moving in clockwise direction, and the least priority group, that is hydrogen, is already away from the observer. So the configuration at that chiral center is R. So here the configuration is R. And a newly generated chiral center may have either R configuration or S configuration. That means if I say this is R comma R, this can be S comma R. At one chiral center configuration is the same, at other chiral center configuration is different. Therefore, you will have a diastereomer for the first compound. And from the second structural isomer, if you see, there is no new chiral center because this is methyl group, this is methyl group. Therefore, no enantiomer, no diastereomer. It has a chiral center, but its stereochemistry is fixed. There the reaction is not taking place. Therefore, we can say no enantiomer, no diastereomer of second structure. Now, let us move on to the third structure, and if you see, this reaction is proceeding through free radical intermediate. See, this is the reaction site. If you see that reaction site, this is the reaction site, and that reaction site, this is proceeding through free radical intermediate, that is sp2 hybridization. One side you have isopropyl group, one is bromine, and another one is ethyl group, and here this is a free radical. Now chlorine radical is going to attack, and this is planar, that chlorine may attack either from front face or from back face. Therefore, the stereochemistry, existing stereochemistry is disturbed, and that is proceeding through planar intermediate, that chlorine may attack either from front face or back face. Therefore, you will get its enantiomer. Of course, stereochemistry is fixed, but there the reaction is taking place, that sp3 carbon is becoming sp2 carbon, planar intermediate, chlorine radical can attack either from front face or from back face. Therefore, you will get enantiomer. And the fourth structural possibility, if you see here, the reaction is taking place at this center, newly generated chiral center. Here already stereochemistry is fixed. This is becoming a new chiral center. A new chiral center is produced, and the new chiral center may have either R configuration or S configuration. Therefore, it will have a diastereomer, because here stereochemistry, and here of course stereochemistry of existing chiral center may be affected, because earlier we gave the priority to isopropyl group. Now due to the presence of chlorine, the priority order may change, but its stereochemistry is fixed, whatever its stereochemistry is fixed. And here the newly generated chiral center may have either R configuration or S configuration. Already there is one chiral center, a new chiral center is produced, then the relation will be diastereomers. And the fifth structural possibility is this one, and here no new chiral center is produced, therefore no enantiomer, no diastereomer. Structurally different isomers, if they ask, that is 5, but total number of isomers they asked, therefore we have to count. This is the 6th one, this is the 7th one, and this is the 8th one. So total number of stereoisomers we got 8, but he said totally 9 isomer products are formed. Therefore, it is a wrong statement. First statement is wrong. Now let us see the second statement. Fractional distillation of product mixture gives 7 fractions. So between 1 and 6, you can see 1 and 6 they are diastereomers. Therefore, since they are diastereomers, so here this is one fraction, this is definitely a different fraction, because diastereomers have different physical properties, and this is one fraction like this. But if you carefully observe, 3 and 7, 3 and 7 are enantiomers. Therefore, they boil at the same temperature, they will be present in the same fraction. And 4 and 8, you can see 4 and 8, they are diastereomers, therefore they have different boiling points. This is one fraction, this is one fraction, and of course this is also one fraction. Structural isomers will have different physical properties. Optical diastereomers will have different physical properties. Geometrical diastereomers will have different physical properties. Enantiomers have same physical properties. They have same boiling point. Therefore, enantiomers cannot be separated from each other by using fractional distillation. And if you count 1, 2, 3, 4, 5, 6 and 7, we got 7 fractions. So, the fractional distillation of product mixture gives 7 fractions. Therefore, this statement is a correct statement. B is correct. Now, all products are chiral. Yes, it has one chiral, it has two chiral centers and unsymmetrical compound it is. Definitely, this is chiral. This is chiral, optically active. There is no meso compound because all are unsymmetrical compounds. There is no question of having plane of symmetry. It is not meso compound. This is chiral. This is chiral. Of course, every compound is chiral. Need not to say individually. All these are chiral. Chiral structures. All products are chiral. They rotate plane polarized light. Therefore, C is also correct. And the next one, all fractions obtained on fractional distillation are optically active, but this one, of course, this is active, this is active, this is active. Now you have to think about a fraction having 3 and 7. The fraction having 3 and 7, the relation between them, they are enantiomers. This is equimolar mixture, equimolar mixture of equimolar mixture of enantiomers, that is racemic mixture, that is optically inactive due to external compensation, due to external compensation, that is optically inactive. But this fraction is not optically active, but of course remaining fractions are optically active. But he is saying all fractions, therefore it is also wrong. So ultimately the correct answer to the question is B,